The golden section search is a technique for finding the extremum of a strictly unimodal function by successively narrowing the range of values inside which the extremum is known to exist. The technique derives its name from the fact that the algorithm maintains the function values for triples of points whose distances form a golden ratio. The algorithm is the limit of Fibonacci search for a large number of function evaluations. Fibonacci search and golden section search were discovered by Kiefer. Basic idea: the diagram above illustrates a single step in the technique for finding a minimum. The functional values are on the vertical axis, and the horizontal axis is the x parameter. The value of has already been evaluated at the 3 points, and since is smaller than either or, it is clear that a minimum lies inside the interval from 2. The next step in the minimization process is to probe the function by evaluating it at a new value of x, namely. It is most efficient to choose somewhere inside the largest interval, that is between and. From the diagram, it is clear that if the function yields then a minimum lies between and the new triplet of points will be, and. However, if the function yields the value then a minimum lies between and the new triplet of points will be, and. Thus, in either case, we can construct a new narrower search interval that is guaranteed to contain the function's minimum. Probe point selection: from the diagram above, it is seen that the new search interval will be either between and with a length of a plus c, or between and with a length of b. The golden section search requires that these intervals be equal. If they are not, a run of bad luck could lead to the wider interval being used many times, thus slowing down the rate of convergence. To ensure that b equals a plus c, the algorithm should choose. However, there still remains the question of where should be placed in relation to and. The golden section search chooses the spacing between these points in such a way that these points have the same proportion of spacing as the subsequent triple OR. By maintaining the same proportion of spacing throughout the algorithm, we avoid a situation in which is very close to OR, and guarantee that the interval width shrinks by the same constant proportion in each step. Mathematically, to ensure that the spacing after evaluating is proportional to the spacing prior to that evaluation, if as and our new triplet of points is, and then we want. However, if as and our new triplet of points is, and then we want. Eliminating c from these two simultaneous equations yields OR. Whereas the golden ratio. The appearance of the golden ratio in the proportional spacing of the evaluation points is how this search algorithm gets its name. Termination condition: in addition to a routine for reducing the size of the bracketing of the solution, a complete algorithm must have a termination condition. The one provided in the book Numerical Recipes in C is based on testing the gaps among, and, terminating when within the relative accuracy bounds. Where is a tolerance parameter of the algorithm and is the absolute value of. The check is based on the bracket size relative to its central value, because that relative error in is approximately proportional to the squared absolute error in typical cases. For that same reason, the Numerical Recipes text recommends that where is the required absolute precision of algorithm equals iterative algorithm equals, let a, b interval of current bracket f. A, F, B, would already have been computed earlier. Let C equals B plus I, D equals A plus I. If F, C, F, D, not available, compute them. If F, C,